Module 1, Lecture C, Configuration Basics. By the end of this lecture, you will be able to use Scikit-Learn configuration options to improve notebook output and estimator display, check package versions and document reproducibility settings for experiments, and apply consistent random seeds and simple project organization habits. Display settings. Configure display. Configuring how Scikit-Learn displays results in a notebook helps make models easier to understand. Clear estimator displays are especially useful when models have many settings or pipelines with several steps. During early experimentation, these display options make it easier to compare preprocessing choices, model types, and parameters. Computational objects can be displayed differently depending on the setting. A simple script may only need a compact text view, while an exploratory or teaching notebook benefits from a clearer display of structure, such as how data move through a pipeline to produce predictions. This added transparency helps learners and collaborators understand key transformations before a model is trained. Configuring display settings in Scikit-Learn makes notebook outputs clearer, more consistent, and easier to share. This helps communicate experiments, compare models, notice parameter changes, and understand preprocessing steps. It doesn't replace documentation or version control, but it makes modeling choices easier to inspect, explain, and remember. Python code, configure display. This example shows how to configure Scikit-Learn estimator displays. It compares compact text output with diagram output, and the printed settings verify which display configuration is active. This setup imports key Scikit-Learn tools for a basic machine learning workflow. It includes configuration utilities for viewing or changing settings, the iris dataset for testing models, LogisticRegression for classification, pipelines for chaining processing steps, and a StandardScaler for normalizing features before training. We load the classic iris dataset with Scikit-Learn, which contains flower measurements used in machine learning examples. Then we check the data array's shape to find how many feature columns each sample has, confirming the dataset is structured as expected for later processing. The code verifies that the iris dataset has the expected 4 features by checking the data array's shape. If the feature count is different, it raises an error to signal that the dataset is not in the required format. This helps ensure the data is valid before any further processing. A pipeline combines preprocessing and modeling into one manageable workflow. Here, the data is first standardized so features are on a comparable scale. Then, a logistic regression model is trained. The model uses a fixed random state for reproducibility and allows up to 200 iterations to help it converge. The code changes Scikit-Learn's notebook display setting so estimators and pipelines appear as visual diagrams, making model structures easier to inspect. It then checks the current display configuration and stores the result, confirming that the diagram setting is active. The code checks the Scikit-Learn version, confirms how model displays are configured, and shows the pipeline steps. The pipeline first scales the data, then applies logistic regression, giving a quick overview of the model's processing flow. The code temporarily changes Scikit-Learn's estimator display style to text using the configuration context function. Inside that block, it checks the current configuration with the getConfig function and prints the temporary setting to confirm the change. After the block ends, the display style returns to the previous global setting. After the temporary context block ends, the code checks Scikit-Learn's global estimator display setting using the getConfig function. It confirms that the setting has returned to its original diagram format, showing that the temporary change did not permanently affect the global configuration. This script shows how to control how Scikit-Learn estimators are displayed. It builds a simple iris dataset pipeline with scaling and logistic regression, then sets the global display style to diagrams. A temporary context switches the display to text, and after that context ends, the setting returns to diagrams. The output confirms the Scikit-Learn version, the active display settings, and the pipeline steps. HTML estimator diagrams. HTML estimator diagrams in Scikit-Learn turn model objects into clear, interactive visual summaries. They show how parts of a machine learning workflow connect, such as pre-processing steps and classifiers, making complex models easier to inspect. This helps users understand the overall structure, explore details when needed, and discuss models more transparently. HTML estimator diagrams are especially useful when Scikit-Learn models include complex pre-processing. Real data often mixes numbers, categories, and text, with each type needing different preparation before modeling. A visual diagram makes the pipeline easier to understand than plain text by showing each transformation and its order. This helps users spot missing or misplaced steps and debug the workflow more effectively. HTML estimator diagrams make notebook workflows easier to understand and share by showing the full model pipeline, including pre-processing and the final algorithm. This helps readers see that machine learning results depend on the entire sequence of transformations, not just the model itself. Using these diagrams supports clearer documentation and more professional presentations. Python code, HTML, estimator diagrams. This example shows a Scikit-Learn pipeline displayed as an HTML diagram in a notebook. The notebook display is controlled by Scikit-Learn's configuration, and the output confirms which display setting is currently active. This setup imports key Scikit-Learn tools for building a simple machine learning workflow in Python. It includes configuration support, the iris dataset for demonstration, tools for applying pre-processing to selected columns, and a pipeline to combine pre-processing with a model. It also brings in standard scaling to normalize features and logistic regression for classification. We load the iris dataset from Scikit-Learn as a pandas data frame to make it easy to work with. The data is then separated into flower measurements as the features and species labels as the target, preparing it for later processing and modeling. Before building the workflow, the code verifies that the feature data and target values have the same number of rows. This ensures every feature set has a matching target. If they do not align, it raises an error to prevent problems during model training. We first collect the feature column names so we can choose which columns need pre-processing. Then, we use a ColumnTransformer to apply standard scaling to the numeric columns, giving them a mean of 0 and a standard deviation of 1. This standardization helps many machine learning algorithms perform more effectively. We create a Scikit-Learn pipeline that combines pre-processing and modeling in one workflow. The pre-processing step applies the earlier scalar to numeric features, and the modeling step uses logistic regression with enough iterations to help it converge. This makes it easier to transform the data and train the classifier together. This setting makes Scikit-Learn display estimators, such as pipelines, as rich interactive diagrams in a Jupyter notebook instead of plain text. It helps make the model structure and workflow easier to view and understand. Fitting the pipeline trains the model on the iris dataset's features and target values. This lets the pipeline learn the patterns in the data and adjust its parameters for prediction. After fitting, the pipeline becomes a trained workflow that is ready for evaluation, prediction, and display as a trained estimator in the notebook. The code reports the Scikit-Learn version to support reproducibility, then confirms that estimator displays are set to diagram mode. This setting lets a pipeline appear as a rich HTML diagram in notebook environments such as Google Colab, making the model structure easier to inspect visually. Displaying the model pipeline in a notebook shows the pipeline object. With Scikit-Learn set to use diagram display, it appears as an interactive HTML diagram, making it easier to understand the preprocessing and classification steps. This script shows how to display a Scikit-Learn machine learning pipeline as an interactive HTML diagram. It loads the iris classification dataset, checks that the features and targets align, scales the numeric features, and combines that preprocessing with logistic regression in one pipeline. After enabling rich pipeline display and fitting the model, a compatible notebook environment can show the full workflow visually as an HTML diagram. Readable notebook output. Readable notebook output makes Scikit-Learn workflows easier to understand and explain. Clear displays of estimators and pipelines help document key choices, such as preprocessing, parameter changes, and model evaluation. This supports students learning machine learning and professionals reviewing or handing off models. Readable notebook output is important for understanding machine learning pipelines, especially when they combine preprocessing steps, column transformations, and estimators. Clear display settings make it easier to see the order of operations, such as whether data is prepared before model fitting and whether the intended model is being used. This reduces confusion and helps learners focus on the modeling strategy rather than decoding complex object descriptions. Clear notebook output makes machine learning work easier to understand, compare, and reproduce. By summarizing the modeling setup and preprocessing choices, it helps reveal mistakes such as incorrect scaling or missing steps. A well-organized notebook supports learning, debugging, explanation, and collaboration. Reproducibility basics. Version checks. Version checks help make data science work reproducible. Results in a notebook depend on the software environment as well as the data and models. And updates to libraries such as Scikit-Learn, NumPy, and pandas can change behavior. Recording package versions documents the environment and helps ensure that analyses can be repeated reliably. Checking and recording software versions helps make results reliable and reproducible. Library updates can change how models run or how data is handled, leading to different outputs later. Keeping version information in a notebook captures the working environment, which is especially important when results are shared, reviewed, or revisited. Documenting software versions is essential for reproducible data science. Record the Python version and important package versions, such as Scikit-Learn, in your notebook setup, conclusion, or project environment file. This makes the computational environment transparent, helps explain differences in results, supports collaboration, and strengthens confidence in your work. Python code. Version checks. This script records important package versions to support reproducible experiments. Its output provides a compact snapshot of the computing environment. We begin by importing the main Python libraries used for data analysis and machine learning. NumPy supports numerical computing, pandas handles data manipulation, Matplotlib and seaborn create visualizations, and Scikit-Learn provides tools for predictive modeling. We create a dictionary that records the versions of important libraries, including NumPy, pandas, Matplotlib, seaborn, and Scikit-Learn. Each package name is paired with its version information, making it easy to track the exact software setup. This helps ensure experiments can be reproduced reliably. The process checks a package version snapshot for missing version information. It goes through each package and, when no version is available, records that package in a separate list. This helps identify incomplete entries, so the environment snapshot stays accurate and reliable. The code verifies that every package version was captured before continuing. If any versions are missing, it raises a runtime error and stops execution. This prevents an incomplete environment snapshot, helping keep experiments reproducible. The code displays a reproducibility snapshot for the notebook by listing each package and its version in alphabetical order. This gives a clear record of the software environment, helping others recreate the notebook setup accurately. This line reminds you to record package versions with your experiment results. Keeping this information helps others recreate the same environment, making experiments more consistent and reproducible. This script records the versions of key Python libraries, including NumPy, pandas, Matplotlib, seaborn, and Scikit-Learn. It checks that each version is available, stops with an error if any are missing, and then prints a clear snapshot of the software environment. Including this version information with experiment results supports reproducibility. Random seed control. Setting a random seed makes computational experiments reproducible. In machine learning, randomness affects steps like data splitting, parameter initialization, and shuffling, so results can change from run to run. A fixed seed keeps the random sequence the same, making it easier to compare results, debug issues, and explain experiments reliably. Use fixed random seeds whenever a project involves randomness, so results are reproducible. This includes train test splits and algorithms such as random forests or gradient boosting. Keeping seeds consistent ensures that changes in performance come from your modeling choices, not random variation, which is especially important when comparing results or working with others. A fixed random seed helps make results reproducible, but it does not guarantee identical outcomes on every system. Differences in software versions, computing environments, or parallel processing can still change results. For transparent and reliable experiments, record the seed value along with package versions and other key details. Python code, random seed control. This example demonstrates how random seeds control reproducibility. Using a fixed seed makes repeated data splits produce the same result, while unseeded splits can vary each time. We import NumPy for efficient numerical work with arrays and Scikit-Learn for machine learning tools. From Scikit-Learn, we use the Iris dataset loader to access a small classic classification dataset. We also use the train test split function to divide the data into training and testing sets so model performance can be evaluated. We load the built-in Iris classification dataset from Scikit-Learn, a common dataset for demonstrations and testing. From it, we separate the input features, which are flower measurements, from the target labels, which identify the Iris species to predict. Before splitting the dataset, check that the features and target labels have the same number of rows. This confirms that every feature set has a matching label and helps protect data integrity. If the counts do not match, raise an error to prevent problems during model training and evaluation. The dataset is split into training and test sets without a random seed, so the split can change each time the code runs. 30% of the data is reserved for testing, and stratification keeps the target class distribution similar in both sets. The resulting test target values are saved for later comparison. The Scikit-Learn train test split function is used to divide the Iris dataset into training and testing data, with the test set making up 30%. Stratification keeps the class proportions the same as in the original dataset. Because no fixed random seed is used, the test set can change each time the code runs. We split the Iris dataset into training and test sets, using the features and target labels, with 30% reserved for testing. Stratification keeps the class proportions the same in both sets, and a fixed random state makes the split reproducible, so results stay consistent across runs. The data is split into training and testing sets, with 30% reserved for testing. Stratification keeps the class balance the same as in the original dataset, and a fixed random state makes the split reproducible for consistent experiments. Use NumPy's default random generator with a fixed seed of 42 to make random results reproducible. Then generate 5 integers from 0 through 9 and store them for use. This gives consistent random output, which is helpful for debugging and testing. This example shows how fixed random seeds support reproducible results. It first records the Scikit-Learn version, then compares unseeded data splits to show they may differ from run to run. It then compares seeded splits and confirms they match when the same random state is used. The seed value, 42, is also used with NumPy's random number generator to demonstrate consistent random output. This script shows why fixed random seeds matter for reproducible experiments. Using the iris dataset, it compares trained test splits made without a seed, which can produce different test sets, with splits made using the same seed, which produce identical results. It also uses the same seed to generate a repeatable sequence of random numbers. The output confirms that seed control makes data splitting and random generation consistent across runs. Experiment notes. Experiment notes are the memory of a data science project, helping you verify, repeat, and explain results later. Record not just the final scores or charts, but the conditions behind them, including the run's purpose, dataset, preprocessing, model, key settings, and limitations. Details such as missing value handling, categorical encoding, and the trained test split can explain why similar experiments produce different outcomes. Reproducibility settings are essential in data science because results can change with package versions, random seeds, operating systems, and other configuration details. Experiment notes should record the environment, library versions, run dates, and key data or feature engineering choices. This helps students and teams compare results fairly and tell whether performance changes come from real improvements or undocumented changes. Good experiment notes should briefly record the question, setup, outcome, and interpretation for each run. They should also explain unexpected model behavior, such as effects from new features or data problems. Clear notes make results transparent, accountable, and easier for others to understand, question, and reproduce. Starter workflow. Load dataset. Loading the dataset is the first step in a reliable workflow. Import the data in a clear, repeatable way, and keep track of where it comes from and which version is being used. If loading involves randomness, such as sampling or splitting, control it so results stay consistent. The goal is to create a stable, well-documented foundation for analysis. Use a fixed random seed whenever your workflow samples data or splits it into training and testing sets. This makes the same rows appear each time the notebook runs, so results are easier to compare, debug, and explain. A seed does not make the model better, but it keeps the data conditions consistent, which is especially important when small data changes can affect performance. Good project organization makes data loading more reliable and easier to repeat. Keep raw data separate from process data. Use clear file names and store files in stable locations. These habits reduce mistakes, protect original data, and make it easier to understand and share how results were produced. Python code. Load dataset. Use a reproducible starter workflow when loading data. Set fixed seeds so early samples can be repeated, and use clear labels to record where the dataset came from. We import Scikit-Learn to support machine learning tasks in Python, then use its iris dataset loader to access a standard dataset for demonstrations. We also import the train test split tool, which divides the data into training and testing sets so model performance can be evaluated. We set the random seed to 42 so random steps such as splitting data into training and testing sets, give the same results each time. This makes the work reproducible and easier to verify and debug. We load the iris dataset from Scikit-Learn as a pandas data frame to make it easy to work with. The data is separated into flower measurements, used as input features, and species labels, used as the target to predict. This keeps the prediction data clearly separate from the answers the model is meant to learn. Before processing, the code verifies that the number of feature rows matches the number of target labels. This check ensures every feature set has a corresponding label and helps protect data integrity. If the counts do not match, it raises an error so the dataset can be corrected first. We split the dataset into training and testing sets using Scikit-Learn's train test split function, reserving 25% for testing. A fixed random seed makes the split reproducible, and stratifying by the target keeps the class proportions consistent in both sets. Repeating the train test split with the same seed shows that the results are reproducible. Using the same test size and stratifying by the target keeps the class distribution consistent, while the fixed random state controls the randomness. If the same test rows appear each time, the seed is working as intended. To confirm the dataset split is reproducible, compare the test row indexes from the original split with those from the repeated split. If the indexes are the same random seed is producing a consistent test set across runs. The workflow records key details to make the experiment clear and reproducible. It notes the Scikit-Learn version, confirms that the iris data comes from Scikit-Learn, and keeps the raw data unchanged in memory. It also prints the random seed, dataset size, and train test split sizes, then shows that using the same seed produces the same test rows each time. This script loads the iris dataset with Scikit-Learn and uses a fixed random seed to make the train test split reproducible. It checks that the feature rows and target labels match, then splits the data and repeats the split to confirm the same test rows are selected each time. The output reports the Scikit-Learn version, dataset source, row count, split sizes, and verifies consistent data handling across runs. Fit model. Model fitting should be a careful, repeatable process where the algorithm learns patterns from training data for future predictions. Before training, confirm that the data is correct, the target is separated from the input features, and pre-processing matches the workflow. Most importantly, avoid data leakage by using only information that would be available at prediction time, such as using only past data when predicting subscription cancellations. When fitting models, set and record a consistent random seed, because many algorithms use randomness, such as starting values or data sampling. Without a fixed seed, repeated runs can produce different results, making performance changes hard to interpret. A documented seed supports reproducibility and keeps comparisons reliable, while still acknowledging that uncertainty remains. Good project organization makes model fitting more reliable and easier to trust. Use clear folders, descriptive notebook names, and notes that record key modeling choices, data versions, seeds, and settings. Keep raw and processed data separate, and distinguish exploratory work from final results. These habits become especially important as projects grow or involve multiple contributors, supporting later scoring and interpretation. Python code. Fit model. Build one model using a reproducible starter workflow. Clearly separate the features, target, data split, and random seed. Then report the software version, key settings, and evaluation results so the process can be repeated. We import key Scikit-Learn tools for a simple classification workflow. the Iris dataset loader, a function to split data into training and testing sets, a decision tree classifier, and an accuracy measure. Together, these tools let us load a standard dataset, train a decision tree model, test its predictions, and evaluate how well it performs. Set the random seed to 42, so results from random steps, such as splitting data, can be reproduced. Then add a short project note describing the script as a starter workflow for fitting a model, which helps with documentation and tracking context. We load the built-in Iris dataset from Scikit-Learn, which contains flower measurements and their species labels. The measurements are used as the input features, while the species classifications are the targets. Separating these inputs from the labels is essential for training a machine learning model to make predictions. Before training, the code verifies that the feature data and target labels have the same number of rows. This ensures each feature set matches one label. If they do not align, it raises an error to prevent problems during model fitting. We split the dataset into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is kept for testing, and a fixed random seed makes the split reproducible. Stratifying by the target variable preserves the class balance in both sets. A decision tree classifier is created with a maximum depth of 3 to keep the model simple and reduce overfitting. A fixed random seed makes the results reproducible. The model is then trained on the features and target labels so it can learn patterns and make predictions on new data. To evaluate the model, we use it to predict labels for test data it has not seen during training. We then compare those predictions with the true labels to calculate accuracy, which shows how often the model is correct on new data. The code reports key details for reproducibility and evaluation: the Scikit-Learn version, a project note, the recorded random seed, and the number of training rows used to fit the model. It then prints the model's test accuracy, rounded to 3 decimal places, to give a quick summary of performance. This script shows a reproducible way to train and evaluate a decision tree on the Iris dataset. It sets a fixed random seed, splits the data into balanced training and test sets, trains a shallow decision tree, and measures its test accuracy. It also reports key run details, such as the Scikit-Learn version, seed, training sample count, and accuracy, so the results can be checked and repeated. Score model. Scoring a model makes its performance measurable after the data is loaded and the model is trained. For classification, the score reflects how often predictions are correct, while for regression, it shows how close predictions are to observed values. To trust the score, keep evaluation conditions consistent, such as using the same random seed for data splits. This helps separate real improvement from random variation. Keep model scores organized by making them easy to find and clearly tied to the exact model, dataset version, and data split used. Place evaluation steps near data loading and model fitting so the workflow is not scattered. Use clear names and record details like random seeds so each score becomes a reliable part of the experiment record. Treat your model's first score as a baseline for comparing later changes, not as a final judgment. To make those comparisons fair, keep experiments consistent by using the same random seed and an organized project structure. This helps show whether improvements are real and supports reliable, reproducible results, which is essential in professional data science. Python code score model. Use a reproducible starter workflow when scoring a model. Setting a fixed seed keeps evaluation splits consistent, and the printed score provides a clear baseline for comparison. We import key Scikit-Learn tools for a simple classification workflow: the Iris dataset, a function to split data into training and testing sets, a decision tree classifier, and an accuracy measure. Together, These tools let us train a model, test it on unseen data, and evaluate how well its predictions match the true labels. We set a fixed seed value of 42, so random steps, such as splitting data into training and testing sets, produce the same results each time. This makes the workflow reproducible and easier to debug. We load the classic iris classification dataset using Scikit-Learn's load_iris function. It provides flower measurements as input features and species labels as targets, giving us the data needed to train and evaluate a machine learning model. The code first checks that the feature data and target labels have the same number of rows. This confirms that each set of features matches one target label before training begins. If they do not match, it raises an error to signal that the dataset is misaligned and should be fixed before fitting the model. The dataset is divided into training and testing sets using Scikit-Learn's train-test-split function. 25% of the data is reserved for testing, and a fixed random seed makes the split reproducible. Stratifying by the target variable keeps the class distribution similar in both sets, supporting a fairer evaluation. A decision tree classifier is created with a maximum depth of 3 to limit complexity and reduce overfitting. A fixed random seed makes the results consistent across runs. The model is then trained on the features and target labels, allowing it to learn patterns and prepare for predictions on new data. We use the trained decision tree to predict labels for the test data, then compare those predictions with the true labels. The accuracy score measures the share of correct predictions, giving a baseline view of how well the model performs on unseen data. The code reports key details for a reproducible model evaluation: the scikit-learn version, the random seed, and the number of test rows scored. It then prints the model's baseline test accuracy, rounded to 3 decimal places, to summarize performance on the test data. This script shows a reproducible way to evaluate a decision tree on the iris dataset. It uses a fixed random seed, splits the data into stratified training and test sets, trains a tree with a maximum depth of 3, and measures test accuracy. It then reports key details such as the scikit-learn version, seed, test sample count, and baseline accuracy. In this lecture, you learn to use scikit-learn configuration options to improve notebook output and estimator display, check package versions and document reproducibility settings for experiments, and apply consistent random seeds and simple project organization habits. In the next module, Module 2, we will go over Estimator API.
Thank you for your attention. See you all in the next lecture.